Good evening, all of you, those who have joined session 6 of IBIPSA education webinar, and Happy New Year to all of you again. Last year we had a successful 5 sessions, and we are in the 6th one now with Christoph and Daniel offering the webinar on indoor thermal quality performance prediction. As usual, this would be around 40 minutes or 45 minutes of talk, followed by question and answers. Those who wish to ask questions should use a chat pane and send me question in writing. Right now, all the participants are in mute mode. After presentation, I will invite one by one and ask a question to Christoph and Daniel. Very warm welcome to Christoph and Daniel. Thanks for offering and agreeing to offer the session. Hand it over to Christoph. Thank you.
All right, so as well from our side, welcome to the webinar on indoor thermal quality performance prediction. Thank you, Rajan. I think we'll talk about, let's say, around 50 minutes it will take. Let's see how fast we are. And yeah, Daniel and me will do this webinar jointly today. Daniel will, by the way, as well co-author the second revision of the book chapter in the book then. Now, thermal ergonomics of the indoor environment concerns several different aspects. So, for example, energy efficiency and indoor climate, which are strongly interconnected, as you all know. So it is quite obvious and subject to the whole IEA Annex 66 project, and as already has been shown by Aditya Madhavi in his webinar, that occupant behavior strongly influences energy consumption. As can be seen from this figure, single variations in room temperature, air change rate, hot water consumption may have different impacts. However, in the worst case, a combination may result in a factor of 4 of the primary energy demand as performance indicators. So we have a strong correlation between occupant behavior and energy consumption. But this may have other implications as well. For instance, typical complaints in office buildings concern issues with the thermal environment, such as too cold or too warm ambient temperatures. However, in offices, salaries are the main matter of expense. They even exceed the maintenance and energy costs during the life cycle. As we can see from the various research activities in the field of psychology, a strong correlation between indoor climate and productivity of persons, or better, the cognitive performance is known. For economical reasons, it is therefore important to provide an optimal indoor climate in order to keep the productivity on a high level. Yet another example here from the perspective of the automotive industry. Electrical vehicles are designed such that they save energy in order to increase the range. As the HVAC within vehicles is the second largest energy consumer, HVAC systems are required that act on a low energetic or exergetic level. So the choice for climatization systems that operate on a local level, meaning close to an individual bodies, such as heated surfaces, ventilated or heated seats, or heated steering wheel, require knowledge of local thermal comfort assessment. So that means what I want to say here is that range and thermal comfort are intrinsically connected design constraints. So the topical context of thermal ergonomics accordingly shows mutual dependencies between the issues of ergonomics, human behavior, and technology. So consequently, this concerns aspects like occupant behavior, environmental psychology, physical responses, health, or room acoustics, air quality, lighting, or from the technology side, it is the construction, the building technology, or the information technology. So to summarize, the whole is a very interdisciplinary research and application topic. Now let us go step by step through the different aspects. The webinar thereby can only provide a short introduction and give an overview, and for further reading, please refer to the book and the references therein. So in order to thoroughly address thermal ergonomics in detail, we need to consider first the impact of the climate on the individual. This concerns the heat and mass transfer between environment and body, sensible and latent heat transfer, as well as acoustics, light, and air quality. Heat and mass transfer takes place by natural or forced convection, long and shortwave radiation, and heat conduction. These heat transfer mechanisms can be measured or calculated, which can be done at different scales and levels of detail. So, for example, for a long-term assessment, empirical heat transfer coefficient models for individual body parts may be reasonable, whereas for a detailed analysis, advanced computational fluid dynamics simulations may be the method of choice. The same applies for measurements. Here, the spectrum ranges from small climate sensors to advanced laser-based air velocity measurements, for example. So having said this, thermodynamic processes within the human body may be neglected or covered by advanced numerical thermophysiological models in detail. The spectrum thereby ranges up to fully parametric individualized models accounting for individual morphological details. But from this point, it is still not clear how the thermal state is evaluated by the human individually. Here, the empirical thermal sensation and thermal comfort modeling comes into play. Such models may further account for physiological adaptation, psychological adaptation, or behavioral adaptation. So in my opinion, this might perhaps be the most essential slide of the whole presentation here, because it really clearly shows the difference between the climatic impact, the aspect of thermophysiology, and comfort perception, which are three intrinsically different things. But now we come to the point to ask, what is thermal comfort and how is this term really defined? Now, the ASHRAE standard defines comfort as that condition of mind which expresses satisfaction with the thermal environment. Personally, I really like the definition of Theodor Benzinger. He defines comfort from a physiological point of view as the absence of driving impulses from cutaneous and hypothalamic receptors causing the body to counteract with physiological adaptations. Well, Adolf Farre-Gagel puts this into the context of conscious actions, indicating that they are not required for controlling the thermal states. And for a resting, unclothed individual, he states that the person perceives ideal thermal comfort at thermal neutral conditions at approximately 30 degrees centigrade ambient temperature. Well, as stated before, a human can exchange heat with the environment by thermal radiation, by convection, evaporation, and conduction. The different modes of heat transfer that constitute the overall energy heat emission thereby depend on the ambient temperature level, as we can see from this figure here. At temperatures below 35 degrees centigrade, the body is able to dissipate heat to the surrounding through evaporation, convection, and radiation. This is, however, as we all know, not possible at temperatures above 35 degrees. Here, the body dissipates heat to the environment by evaporation only. Consequently, for example, for working in hot environments, heat stress can be expressed in terms of evaporation or better, the sweat production rate. On the other hand, in a vehicle environment, such as a car, sweating shall be actively avoided under any circumstances in order to avoid discomfort by skin wetness. Now, how does a human perceive temperature in general? Reactions of the human thermoregulatory system towards thermal stimuli are coded in fire rates of thermoreceptors. We distinguish between receptors for cold, which are mainly positioned at the body surface, and warm receptors, which are positioned inside the human body. The ranges where receptors are active differ. At skin temperatures above 34 degrees, warm receptors are active, and at skin temperatures below 34 degrees centigrade, cold receptors are active. Outside these ranges, receptors for pain are existing as well. Within the so-called thermal indifference zone, here indicated in yellow color, a minimum level of thermoregulation is required in order to maintain the body core temperature on a constant level. Here, both receptors are active, which can be generally associated with a state of thermal neutrality. The picture of comfort assessment becomes even more complicated as cold receptors are inhomogeneously distributed across the human body. This expresses the different sensitivities of the individual body parts, and as we all know, this needs to be reflected by a local comfort model as well. Well, as most of you probably know, the most prominent thermal comfort model, the model of Ole Fanger from Denmark, which emerged in the 1970s, I would like to point out by this chart here that the history of thermal comfort research started almost a century earlier. Lots of the formula to predict thermal comfort and devices to measure different physical quantities emerged during that time. The main scientific breakthrough was the consideration of the heat balance of the human body and the correlation of the former with the statistical mode of sensation of test subjects. Several of the early instruments, such as the Carter thermometer, for example, or the artificial head, form the layout of today's measurement devices as they try to imitate an artificial body of the transient behavior of the physiological regulation. Unfortunately, we do not have much time here to walk through every single detail here, so I would like to refer to the literature. Now, how do we come from a physical description of the indoor climate to a performance indicator expressing local or global satisfaction with the thermal environment or discomfort? In a simplistic approach, we would take a minimum set of environmental and personal parameters and correlate these through a model, however this might look like, with a reasonable performance indicator. I would call this approach a black box approach. However, we might as well understand and model each of these processes separately and at various levels of detail in order to turn this black box model into a white box one. We will in the following talk about some of the widely known approaches and indices. One of the newer publications published by George Chapanis and Dusan Fiala shows that more than 160 indices with respect to thermal comfort and heat stress evolved in the literature in the past 100 years. Each of them has its specific field of application, whereas the majority is dedicated to heat stress. So, for example, we have indices like the wet bulb temperature, which links the effect of evaporative heat loss to dry bulb, or the effective temperature, which is similar to an equivalent temperature, but as temperature of an imaginary environment at 100% relative humidity, or the heat stress index, the HSI, which is the ratio between the heat load and the evaporative capacity of an environment, or the WBGT, the wet bulb globe temperature, which is basically a linear combination of wet bulb, globe, and dry bulb temperatures for heat stress management, which as well as standardized, as you know, in ISO 7243. I think the title is something like the estimation of heat stress on working men in hot environments. And then we have the standard effective temperature, or the PHS, the predicted heat strain index, which is the calculated sweat production for temperature regulation as an index of thermal stress and physiological strain. Well, it can be used to adjust exposure time, for instance, in practice, or the UTCI, the Universal Thermal Climate Index, which is an index based on physiological simulation modeling, covering a whole range from heat to cold, and which has been designed for weather information services and for epidemiological studies. And then we have a new one, a totally ridiculous uniform model performance index, which is called the Trump index, which emerged in social media recently, but to my knowledge, that is not yet widely used in practice yet. So what we can do now is grouping the various indices according to their application on a local or global scale, meaning for individual body parts and for the body as a whole, and with respect to steady state or transient conditions, and with respect to homogeneous or non-uniform environments. Hui Chang's model, as well as Dusan Fiala's DTS, are based on a physiological background. Now, in this regard, Hui Chang relies on a kind of fuzzy logic approach, whereas Dusan considers transient effects with some kind of a remembering function, which for hot environments stores the maximum skin temperature gradient whose influence vanishes over time. Now, some of these models are coupled to a thermoregulation model, which is needed as input. Now let us further detail the well-known model of Ole Fanger. The basic idea of that widely applied model in practice is the formulation of the heat balance of the human body as a whole, starting from 4 physical input signals, meaning the mean radiant temperature, the air temperature, the air velocity, and the relative humidity, and 2 or respectively 3 personal factors, such as the activity and the clothing insulation level, and the workload, which is typically 0. Now, if the so-called thermal load, meaning the storage term, as a net difference between heat production and losses is in equilibrium, a thermal neutral state is assumed. And based on a large-scale survey with test subjects, I think at that time it were around 1,300 subjects, a statistical correlation was performed by Fanger to correlate the load with the thermal sensation of a large group of persons, indicating the satisfaction with thermal conditions. The model is therefore applicable at steady state conditions, near thermal neutrality, and for the body as a whole, which clearly restricts it mainly for the application in buildings. The so-called PMV index, the predicted mean load, is evaluated by the 7-point ASHRAE thermal sensation scale, shown here on the right-hand side. Now the PMV index, that means the thermal sensation, can be transformed into an index expressing the level of dissatisfaction for this specific thermal situation. The PPD accordingly reflects the percentage of dissatisfied. As can be seen from the figure, PMV and PPD are correlated by an inverse Gaussian curve, where a minimum PMV equal 0 corresponds with a PPD of 5%. This means that even at thermal neutral conditions, as you can see from the curve, statistically, almost 5% of a group of persons remain dissatisfied. Other studies reveal a tendency to shift this curve into the warm area, such as the results of Erhard Meyer. The minimum PMV here is at +0.5 and the PPD at 15%. Now, differences between both findings might be attributed to the fact that the researchers did not explicitly ask their subjects for thermal acceptance, which is normally done in today's thermal comfort assessment studies. So in this regard, Fanger defined all PMV values between -1 and +1 as comfortable, whereas Meyer defined all PMV values unequal 0 as uncomfortable, which is clearly a difference. Let us now demonstrate the application of the model in reality. This video shows a student survey at our university, the RWTH Aachen University, during a lecture course in summer 2016. Now, prior to the study, we informed students about the meaning of the voting scale, as shown here in the video. The study was performed in an air-conditioned auditorium, and we asked a group of students according to their actual thermal sensation. Now, as can be seen from the video, students wore different clothing combinations with different insulation values. And the students evaluated the sensation according to the questions from the moderator. So as you can see here, we see the answers, for instance, here to the question, does anyone feel neutral, equals 0, which is then put into the chart here at the position 0. And we continue that with the next question, does anyone feel slightly warm? Again, we put that at position 1 here into the diagram. And last question, does anyone feel warm or hot? Which is not answered by anyone, so we see a 0 here in the diagram. Now the results of the two surveys are summarized in a table, which you can see here, and subsequently we calculated the averaged predicted mean vote, which gives a value of approximately 6% of the corresponding PPD in that case. This, however, correlates well with the category A building according to ISO 7730 and indicates that the air conditioning in that room seems to work well at that time. Now, this example has shown that if the air conditioner runs a predefined algorithm according to the PMV, and if other design constraints according to local thermal effects are considered, the real-life prediction will follow the path of the model. I think that's not surprising and indicates that the system is running properly. This accordingly applies for mechanically ventilated buildings. In free-running or naturally ventilated buildings, however, this situation might be different. Here it was observed by Richard Didier, by Gail Braga, Michael Humphreys, and Fergus Nicol that people would accept higher operative indoor temperatures in summer if they can adapt themselves to the climatic situation in order to reduce thermal strain. The so-called behavioral actions may comprise the opening of windows, wearing appropriate clothes, adjusting the schedule, closing roller blinds, installing local fans, and the such. However, adaptations may as well concern psychological effects, which are linked to expectations like the weather was bad the last 2 days, it might be bad tomorrow too, or physiological adaptations which are linked to the acclimatization and physiological issues such as non-shivering thermogenesis. So as today, the interplay between these adaptation processes and the driving impulses are not yet fully understood and still subject to research. Within the so-called adaptive modeling approach, a simple link between the history of the outdoor temperature in the standard ISO 15251, it is the exponentially weighted mean outdoor temperature, is put into context with the acceptable range of operative indoor temperatures. From the thermal comfort temperature, which is here a curve in the center, which is not shown a center between those lines, different categories are defined. And outside the lower limits of the diagram, so which would be on the left side here, starting from the lower category, the conventional ISO model is then valid. It is interesting, I think, to note that several researchers have shown that the adaptive model can be derived from Fanger model as well, if models for behavioral actions such as clothing selection are further considered. As well, Darren Robinson and Haldi explain in a paper from 2007 quite nicely that the slope of the adaptive curve may be explained in terms of aggregated individual adaptive processes. As well, Ole Fanger discussed some kind of extension of this model with the so-called expectancy factor. Now, in the following, we consider the application of such models. Here, for example, the adaptive model in building simulation. Here, we see the results of the thermal simulation of a sample room within an office building where maximum daily values of the operative indoor temperatures are plotted against a sliding window of the weighted mean outdoor temperature of the respective weather data file. Now, if a single value drops out of the defined range, as does happen here as well, the building is downgraded into a lower category accordingly. So in our tool, we can visualize results in a calendar type diagram indicating if such incidents show up systematically or not, and when such overheating occurs. I think this is a very descriptive method to analyze such models. This brings me again to an important point in that presentation, namely which type of simulation model do we really need or do we have in order to assess which type of thermal comfort analysis. This is indicated in this figure. Now on the left side, through the different phases within a planning project, different levels of development of the model, such as a BIM model, for example, become available. For energy certification, steady-state balancing methods may be appropriate. With these methods, however, only heat balances can be drawn. Information on surface temperatures, air temperatures, the airflow distribution, or even the air velocity field cannot be captured with these methods. In order to reveal further details, a dynamic multi-zone simulation model with airflow network may be used. So such models, as you know, make averaged air temperatures, surface temperatures, and as such at a resolution of a node in a thermal zone available. Operative temperatures can accordingly be computed. However, as well, these models do not reveal any detailed airflow information which would be required for a draft risk assessment. Therefore, a further complex and sophisticated computational fluid dynamic model needs to be created and linked with a thermal zone model in order to get the boundary conditions. Having such information in further detail would be the use of a coupled detailed human thermoregulation model. So in summary, depending on the required levels of detail, the whole situation ranges from a simple heat balance model up to a coupled multi-physics model at various scales and levels involving advanced stuff for tool coupling such as co-simulation. Now in the following slides, we will have a deeper look into the levels of detail of the respective simulation methods. So in this application now we see the thermal simulation of a single office room using a zonal building simulation model. Now we run through the annual performance simulation where the frame on the left-hand side displays the daily overheating hours. The geometry model is shown on the right, and in the center frame we see from top to bottom the operative temperatures in the adaptive comfort diagram, where the categories are indicated by the lines, and then the operative indoor temperatures at the bottom with the balance of the heat transmission over time in that case, which we can modify later. Now, having completed the annual performance simulation and finding out that we have some excessive temperature hotspots observed, we can now further refine the time resolution. Let us now change the balance to display the internal solar heat gains, and let us select one of the hot days from the calendar view. Now we get a closer look of the problem with the solar shading in that case, obviously, which we can amend accordingly in the model and restart it. So in summary, with such a zonal model, we can gather information on the average air and mean surface temperatures over time, which form the input for calculating the operative temperatures for the thermal comfort assessment. We find data of local air velocities and as such cannot be retrieved from such a model. In this model setup, the thermal multi-zone model is now further refined. Here, a ray tracing algorithm for solar radiation tracking in combination with a detailed window model is used. So the incident solar radiation is tracked until the surface of an artificial thermal mannequin, as we can see here. So we did that stuff some years ago on our own. The simulation takes more computational effort, obviously, but gives us precise information concerning the solar radiation distribution at the artificial body surface. When we come to a detailed thermal analysis of the heat fluxes and to and from the body, as well as the convective heat transfer is important. So in this example, we see on the left-hand side the temperature distribution of the thermal plume above the head of a numerical mannequin in reality. The temperature field was computed in MATLAB by solving the convection diffusion equation numerically based on a measured flow field, which we can see on the right-hand side. The right frame has shown the corresponding airflow velocity field, which has been measured by an advanced stereoscopic particle image velocimetry method in a lab. So I think this movie shows nicely the turbulent nature of the natural convection regime around the human body. In the last step, and now knowing about the heat transfer mechanisms at the body surface in detail, we can simulate the human thermoregulation by a detailed numerical thermophysiological model. In this specific example here, the commercially available finite element-based used tool Thesis FE was used, and we linked that with an own development, a graphical front end, the so-called virtual climate chamber. So with this tool, we can vary the ambient thermal conditions and monitor the dynamic answer of the human thermoregulatory system. So I hope you get the idea, which we would like to show here. So in the previous examples, I think we have covered the whole range of models, starting from coarse and ending up with a fairly detailed representation. Now, in order to capture the thermal state of an individual and to assess local thermal comfort, as well, detailed measurement techniques can be applied. And at this point, I hand over to Daniel now.
Well, thank you, Christoph. I will start this section with a short excursion to the automotive sector. As it is well known, car cabins are confined spaces in which highly asymmetric boundary conditions are present. Thus, whole body approaches for the assessment of human thermal comfort are no longer valid. Here, a measurement system that is based on flat heated sensors, according to ISO 14505 Part 2, can be used to objectively measure the local thermal comfort on individual body parts. The system itself is based on the measurement of body part-specific equivalent temperatures that represent the temperature of a homogeneous room in which the corresponding body part would experience the same dry heat exchange as in the actual non-uniform environment. In other words, it represents the transfer of an inhomogeneous climatic situation to a homogeneous one in which the airspeed is assumed to be close to zero. I want to mention at this point that the assessment of body sections that are in physical contact with solid objects are not accessible with the current version of the measurement equipment. For this, however, ISO 14505 describes other methodologies, such as, for example, the use of a heated mannequin. So, as already mentioned, there are different ways to measure the equivalent temperature. However, the above shown system is based on the following measurement principle. In our system, we use a constant heat flux to heat up the green-colored sensor surface. Convection and radiation cause a cooling or rewarming of the corresponding surface, which leads to the so-called resulting surface temperature RST. That can be measured and directly transformed to the equivalent temperature using a simple linear approach. The correlation between the equivalent temperature and local thermal comfort was originally developed by Nielsen in 2004. It is represented by the so-called local mean vote LMV, which represents a mixture of the thermal sensation and thermal comfort votes. In this regard, the LMV is represented by comfort zones, ranging from 1, meaning too cold, to 5, meaning too warm, where the digit 3 is the neutral point. There are two different LMV ranges included in the standard that are applicable to clothing combinations for summer and winter. Now, this chart summarizes the quality of the existing modeling approaches. We differentiate between boundary conditions, predictions, validation, and standardization. What we can see is that for steady-state conditions, models perform well. Whereas, for example, for contact-related problems, not a single model produces results of practical relevance. For the predictions, models show a high diversity and some of the models are standardized. For example, the DTS model is well applicable for the prediction of global thermal comfort, but does not evaluate thermal comfort on a local level. In contrast, Hui Chang's model, for example, is well suited for local thermal comfort prediction, but is only partly applicable for the prediction of thermal comfort for contact-related body areas. In summary, a model needs to be carefully selected depending on its intended field of application. Hui Chang's model quite nicely describes the interplay between local and global thermal sensation and comfort perception. The model as such has a physiological background and considers the concept of alesthesia, meaning that a thermal comfort-related stimulus is perceived as pleasant if it improves the body internal energetic state. Starting on a local level, the local thermal sensation is calculated based on a deviation of local skin temperatures from the predefined set point. As we can see from the upper left picture, the model considers the overall thermal state of the body. This state is expressed in the mean skin temperature and shown here by the two indicators body colder and body warmer. Global thermal sensation represents the integral value of the body part specific sensation votes and modifies the local thermal comfort perception. Due to the different sensitivities, the different body parts have different weights, which is indicated by the bottom figure. Based on local sensation, local comfort is evaluated, where again the global sensation modifies individual curves. Finally, the global thermal comfort is retrieved by a rule-based model. So, in order to overcome some of the deficiencies in the area of contact perception, Caroline Schmidt at our institute recently developed a new model which we call balanced comfort model. combines the heat balance ideas of fungus with the model concept of Hui Chang. The BCM itself is implemented in Modelica and considers heat transfer mechanisms on a global level as area-weighted values of the local levels. It considers heat transfer on the local level as well. The body part-specific energy balances are calculated via fungus set of equations. It thereby considers explicitly the contact areas of persons. This expands fungus approach accordingly. Hui Chang's set of equations is then used to calculate thermal sensation and comfort on the outcome of the performed energy balance calculation based on fungus set of equations. Even though those physiologically motivated models are important to assess complex transient and non-uniform scenarios, from the building performance simulation perspective, robust and easy-to-use models are required, which become available through ISO 7730 and ASHRAE 55. With this, I hand over again to Christoph.
Yeah, okay. Thank you, Daniel. So we go back again from the fairly detailed models to the models of ISO 7730, which we can use in combination with building performance simulation. Now, in addition to the already mentioned Funger, PMV, and PPD model, the standards consider 4 local thermal discomfort models, which can be used in addition to the global model. One of them is the draft rating model, which is basically an empirical equation correlating the local air temperature, the local air speed, and the turbulence intensity, which is the standard deviation of the fluctuations of the velocity field. Now, from this formula, shown here in yellow, we can calculate the percentage of dissatisfied, which we can use in simulation. So, for example, some time ago, we did the thermal analysis of a multi-story office building in Switzerland. And here, a thermal multi-zone model was used in order to compute boundary conditions, which were then used as input for a computational fluid dynamics model. So on the left-hand side, we see the velocity field from the CFD post-processing for the winter case. And using the data for a horizontal plane, here shown on the right-hand side, the draft rating was calculated and visualized with colors at the plane and using the formula we have just seen. Now the figures reveal that at parts of the lower atrium, a severe risk of cold downdraft exists and indicates that here some constructive countermeasures need to be installed. Well, you know how that works, such as small heaters, for instance, alongside the window, for example. Another local thermal comfort phenomenon is the vertical temperature difference. The vertical temperature difference is a typical incident in indoor ventilation setups when air conditioning is in place. People do not tolerate a hot head and cold feet, for example. The temperature gradient typically is evaluated between head and ankles. As well, for these vertical temperature differences, the standards recommend a respective maximum temperature delta of 8 degrees centigrade and provides a formula how to calculate the correlation between delta T and percentage of dissatisfied. To my knowledge, this formula is not shown in all standards. I think it's not shown in the ASHRAE standard, but in the other standards, this formula is given. Now, as the standards limit the application of several climatization strategies drastically, at the EON labs here at RWTH Aachen, recently several tests with subjects in a special and highly modular thermal test chamber were performed and evaluated. We will briefly show some of the results of our colleagues at the following slides. A typical incidence of situations with vertical temperature gradients occur in connection with displacement ventilation. The idea is that hot air and contaminants are withdrawn from the upper part of the air following the path of natural thermal convection. So fresh air is then supplied at the bottom level. Summarizing the current state of the literature, as shown here by Martin Mühlenkamp, it is obvious that the definition of ASHRAE and ISO standards, here printed as black bold line, limits vertical temperature gradients based on the available knowledge from literature at that time when the standard was formulated in the early 1980s for the first time. Please note that in this figure here, the x-axis represents the vertical temperature stratification delta t by delta y, and not the temperature gradient between head and ankles as is usually used in the diagrams in the standard. The Aachen Comfort Cube was constructed as a highly modular environment to meet several real-world application scenarios such as aircraft cabins, vehicle cabins, or other spaces. The cube allows to model any kind of temperature asymmetry and is characterized according to its construction by very fast thermal reaction times. Several different ventilation strategies may be implemented as well. Here we see the control panel in the interior. Up to 3 seats may have place. In the general setup of the test series, 126 subjects were tested. In the first experiment, a displacement ventilation for mean operative temperature of 23 degrees was maintained at a constant level, whereas the vertical temperature gradient was varied between 1 Kelvin per meter, 4.5, 6, 8, and 12 Kelvin per meter, as indicated by the series of curves here. In a second experiment, the gradient was fixed and displacement ventilation was considered at a mean temperature of 20 degrees and at 26 degrees, in addition to the former 23 degrees centigrade scenario. Test subjects were asked for their sensations by a questionnaire with respect to local thermal sensation, comfort, and thermal preferences. The results reveal quite clearly that the prevailing definition of the acceptance rate according to vertical temperature gradients is much too conservative. The results of Martin-Milling-Kamp indicate a quasi-linear correlation, which mainly depends on the mean operative temperature rather than the gradient. With these results, displacement ventilation seems to be feasible over a wider range of applications. Now, to summarize that, other issues of these local comfort phenomena address discomfort caused by warm and cold floors, like shown here, or for local comfort phenomena which can be addressed by the standard as well. So now I will hand over to Daniel for the last part.
Thanks again, Christoph. So, as Christoph has already shown in the prior slides, there are many applications in which more or less detailed numerical human models are used in order to simulate the heat exchange between the human being and its physical ambient. Reasons for this are diverse and mainly address the interest of researchers in understanding the human thermoregulatory response to diverse ambient conditions, meaning uniform and non-uniform, transient or static conditions. In this regard, numerous numerical human models arose over the past 70 years. From this slide, we can see that there are generally 4 different model categories, whose level of detail reach from simple empirical equations, one-node models and two-node models, up to more complex multi-element models. A common feature of nearly all these models is that they are based on a general heat balance equation that represents the heat exchange between the numerically approximated human being and its physical ambient. One of the most prominent one-node model is probably fungus model. Here we can regard the activity level as some kind of energetic approximation of a human being. From the category of the two-node models, we probably know best the two-node Pierce model developed by Gage, which is generally based on the same mathematical equations as fungus model, but considers an actively controlling part. Among the most well-known multi-node models is Stolvik's model. It serves as the base for various models such as the Tanabe model or ISD Fiala model. Stolvik further subdivides the anatomy into interconnected segments and different tissue materials. The ISD Fiala model as multi-element model is probably the most popular humanoid. It is characterized by a high level of detail and high prediction accuracy over a wide range of ambient conditions. Here we can see the categories of the models as well as their corresponding characteristics. As can be seen, a one-node model idealizes the human being as a single node or an empirical equation, whereas a two-node model is characterized by the subdivision of the human anatomy into 2 interconnected cylinders. Such models often follow the core shell principle. Multi-node models are characterized by the increased number of shells and segments that are used to approximate the human anatomy. In addition, they include an explicit assignment of the energy balance equation to each discretization node. Multi-element models have many structural analogies to the multi-node models. That is why it is often hard to distinguish between the two. However, the multi-node models use finite difference or finite elements to solve the transient heat conduction equation for each single discretization node, which increases the accuracy of the predicted temperature profiles within the corresponding body segments. This table here gives an overview of the different humanoids with respect to their field of application in connection with their level of discretization. The table is just to show you the huge variety of the various models. As we do not have time to go into detail here, we would like to refer to the literature. Generally, the published models of the literature represent an average human being that is typically male. So far, only a few authors address model individualization. However, this will become more important in the future in connection with the trend towards the development of human-centered HVAC systems. Here we can see that mainly the more complex multi-element models address this adaptation aspect so far, which can be related to their high level of detail and the realistic modeling of physiological and anatomical aspects. Even though promising progress has been made so far in that field, there are still many open questions concerning the key parameters that mainly influence the human thermal behavior. Due to this reason, we recently implemented a fully scalable multi-element model called Morpheus in the acausal equation-based modeling language Modelica. Here, Morpheus is an acronym for Morphological Human Energy Simulator. The implementation concept of Morpheus follows a component-based modeling approach in order to quickly adapt it to individual anatomical and physiological characteristics. Its mathematical structure is a hybrid between the Viala and the Tanabe model. The entire human thermoregulatory system was basically split into three components. The passive system contains a geometrical approximation of the human anatomy. It accounts for non-uniform ambient conditions by subdividing individual body segments into sectors. Heat exchange is modeled between a central blood pool and each individual tissue layer. Countercurrent heat exchange between arteries and veins is considered as well as a complex skin blood flow model. The passive system itself is connected to the active system, which represents a human central nervous system and which contains the thermoregulatory mechanisms, shivering, sweating, vasoconstriction, and vasodilatation. A special characteristic of the model is that it can be used within experimental setups for the real-time prediction of the human thermoregulatory response. This is possible due to the model export for co-simulation. On this slide, we see the general model facts, and which are summarized here. It can be seen that the anatomical part consists of 7 different tissue materials and is split into 19 body segments. Except for the head, the different segments are represented by concentric cylinders. To the end of this presentation, let us show you some advanced crazy stuff where we make use of all the developed models. One scenario is the use of model predictive control for the climatization of electrical vehicles. We acquire different sensor data together with thermal infrared imaging, which are transferred by a canvas-like system to a database. Our thermophysiological solver Morpheus operates as a functional mock-up unit in a co-simulation environment together with our Modelica comfort library. The virtual human forms the basis for the HVAC control and the feedback system. This slide exemplarily depicts the interaction between the hardware system described in the former section and a real human being. As mentioned above, the system is normally used to assess the effect of the dry heat exchange on a person's thermal comfort. For demonstration purpose, however, we touch the sensor surface in order to show the interaction between the measurement and the feedback system. What we can see on this slide is the calculated equivalent temperature for the face region. It is coded in a color information that reaches from blue, which represents uncomfortably cold, to red, meaning uncomfortably warm. Finally, we would like to show the last example. Here we can see the body tracking algorithm, which is coupled to an infrared camera that allows to track individual temperature region at the person's body surface, thus enabling the prediction of local and global thermal comfort when combined with the above sketched thermophysiological solver morphos and the balanced comfort model developed by Caroline. At the left-hand side, we see the monitor application, which is basically a web-based service that enables to selectively monitor parts of the internal database with any kind of mobile application. The communication between the sensors and subsystems is organized on an XML scheme and makes use of the CAN bus protocol used by industry. Okay, guys, that's it from my side.
Okay, now let us come to the end. We might like to summarize this presentation with this slide, which you have already seen before. So thermal ergonomics comprises measuring or modeling and simulating the heat and mass transfer between the environment and the body, sensible and latent heat transfer. So from the climatic impact, we may have used then a black box model to directly assess thermal comfort, as Bangel did. On the other hand, we may open the box of Pandora and try to really understand the dynamic thermophysiological system of the human being in detail. In order to assess the acceptance of the climate by the individual, empirical models of thermal sensation and thermal comfort come into play. Such models may further account for physiological adaptation, psychological adaptation, or behavioral adaptation. The context of thermal ergonomics therefore shows many mutual interdisciplinary dependencies between the issues of ergonomics, human behavior, and technology. Okay, guys, now thank you all for listening. We do hope that we sketched the major issues here and would like to refer to the book for further reading and are open to questions. Thank you. Thanks.
Hi, this is Rajan Raval again. Thank you, Christoph. Thank you, Daniel. That was very good overview of the chapter. So far, I have received 2 questions. One from Dimitri and second from Jarampoulos. So I will unmute Dimitri. He'll be able to ask questions directly. Dimitri, I have unmuted you. Can you hear us?
Yeah. Okay. Hello.
Yeah.
Thanks for the
Please
presentation.
go ahead.
I've got one question regarding standardization of modeling procedure of modeling of thermal comfort. So the question is there any standards under development which outlines procedure of CFD thermal modeling in a similar manner as for whole building energy modeling, as we use, for example, ASHRAE 19.1 Appendix G. So is there any standard which will cover modeling procedure? The question is because there are many ways of using turbulence models of transient, transient simulations. And obviously you can get completely different results depending on the procedure. And any standard would help a lot. Okay, thanks.
Okay, thank you for that question. I must say, to my knowledge, in the building sector, I really need to think about that, if there is any standard. I think to my knowledge in that depth, not. But I remember an approach in the standardization work, which was an extension of the ISO 14505, which is basically this equivalent temperature approach, where a calculation, a computation method was proposed some years ago, where exactly this standardization approach was about to happen. To be honest, I'm not a friend of that, because you know, if you standardize something like this, the state of the art, how to use which type of method, then you see sometimes issues like you need to use a K epsilon model with these and these settings, which is by that time perhaps the state of the art, but yeah, the situation changes. And in my point of view, I don't know if this really makes sense. We have, you know, in CFD work, we have several benchmarks, benchmark cases. I think that's perhaps the better answer to the question. So if you're using a numerical code, you should be sure that, well, first of all, the persons that make use of that code have the respective skills to use it. Then that the code has been validated against, I don't know, some test cases, then that your solution is mesh independent, that you can capture the thermodynamic effects, etc., which is usually characterized by some dimensionless quantities like Nusselt number correlations, for instance, for the convective regime, etc. So I think that's much more efficient. And to be honest, I'm not really a friend of standardizing such things because that's basically engineering work, what we're doing here. And I think we should not standardize everything here. I hope that perhaps answers the question a bit.
Yeah, I think this answer is, it makes sense a lot. Okay, thanks.
Okay, thank you. Second question.
Yeah, we have a second question from Charalampos, and on his behalf, I'll ask question. The question is, the library for thermal comfort calculation in Modelica is available?
Good question. Next question. No, just kidding. I will answer it like that. The library we have shown here, with especially with Caroline's model, this is currently not open source, but it contains a lot of state-of-the-art models. Where we are currently doing a lot of research as well with industry on that matter, and some of the latest models we did not yet publish, but I would like to ask it differently. We had this whole Annex 60 project, and within the Annex 60, a wonderful thing happened, because there a unification took place of the 4 major worldwide Modelica libraries. There were the libraries of the colleagues from Berkeley, the library from the colleagues of Leuven, the colleagues of Berlin, and the Aachen library. And people established a unique set of base classes, a set of unique base classes. I think we have much more than 200 common objects now in this library, which form a common basis that you can use objects all or over these libraries. Now these libraries are basically dedicated to building performance simulation and controls, etc. And we did not yet put our models, our comfort models, in these libraries, but this is likely to happen within the next month or the next year, perhaps, for the base models. Yeah. So our personal library, to answer it shortly, is currently not available, but this is something one can discuss bilaterally, I think, at any time.
Okay, so this is Rajan again. So any work on Modelica and what you described, would there be any literature available on NX website? Can they refer to website for further information, Christoph?
Yeah, well, the information on the Annex 60 is disseminated at the website. Yes, we have this. Or I don't know if I have it in mind. But if you Google Annex 60, IEA-Annex 60 or something.org is the website. And as you know, this Annex 60 project is now continued as the IBIPSA 1 project, which is just about to form and which will start in fall that year. It will be an international collaboration framework again, in order to further enhance Modelica models and functional mock-up co-simulation standards, and BIM to Modelica translators and the such. So I think the IBIPSA is the right platform for the dissemination of such models, and we can further discuss that, of course.
Okay, fantastic. Thank you. We have not received any more questions. There are a lot of comments and questions based on whether this would be available, the presentation would be available or not. So I wish to inform participants that we have recorded this, and this would be available on YouTube channel, IBIPSA University channel on YouTube, probably next or later next week. You will be able to access that. So with this, I wish to conclude this particular webinar. Thank you very much, Christoph and Daniel, for your efforts and spending time with us, offering this wonderful session. Thank you very much. Thank you.
Thank you all for listening. Have a good day. Bye.
Thank you.
Bye.
Bye-bye.